We're now going to look at question 3 of the A-level further statistics paper from 2022. It looks like quite a long question, split into 5 different parts and with 14 marks available. Just like any other long questions, let's take this step by step. We're going to look at part A first. It says, during the summer, Mountain Rescue Team A received calls for help randomly with a rate of 0.4 per day. Part A is asking us to find the probability that during the summer, Mountain Rescue Team A received at least 19 calls for help in 28 randomly selected days. Now, there are a few things I'm highlighting in the question. First of all, the rate of 0.4. And the important thing is to note that the rate is per day. Quite often when we are given certain Poisson distribution, duration, the time period changes. In the first paragraph, we've got per day. In part A, we've got 28 randomly selected days. Therefore, we need to be converting the parameter or the mean value from 0.4 to something that's suitable for 28 randomly selected days. So let's answer part A together. I'm going to name a number of different random variables. First of all, I'm going to call something D. So D is the number of calls received per day, and D follows a Poisson distribution with mean 0.4, parameter of 0.4, and D is the number of calls received per day. Okay. What about 28 days? For Poisson distribution, we can simply multiply the mean. So for 28 days, I'm going to call it M, approximately a month. Follows a Poisson distribution 24 multiplied by 28, which means that the random variable M follows a Poisson distribution with mean 11.2. So M is the number of calls received in 28 days. Okay. Question A is asking us, what's the probability that during the summer, Mountain Rescue Team A received at least 19 calls? The probability that I need to be writing out is probability of M greater than or equal to 19. The other thing we need to be paying attention to when writing out an inequality is whether to use greater than or equal to. So in the question, it says at least 19. At least 19 means I include 19, and therefore I'm going to write M greater than or equal to 19. So we can plug this into our calculator, Poisson distribution with mean of 11.2. Writing this out slightly differently because it's a discrete distribution. So it's 1 minus the probability of M being less than or equal to 18. So that's 1 minus 0.9792 based on my calculator. And the answer is 0.028. And that's my answer to part A. Now let's look at part B. Let's read the question first. The leader of Mountain Rescue Team A randomly selects 250 summer days from the last few years. To record the number of calls for help received on each of these days. Part 2 asks us to use a Poisson approximation to estimate the probability of the leader finding at least 20 of these days when more than one call for help was received by Mountain Rescue Team A. Quite a number of different numbers there. So we've got 250 summer days, we've got at least 20 of these days, and we've got one call for help. We're going to break that down step by step. First of all, let's find out what I call the base event. Base event is more than one call for help in a day. What's the probability of more than one call for help? So remember, the number of calls for help is D, and D follows a Poisson distribution with parameter 0.4. So what's the probability that there's more than one call for help each day? More than one call for help means that I want a probability of D greater than 1. And again, to work that out in our calculator or from these tables, this is simply equal to 1 minus probability of D less than or equal to 1. We can use the definition of Poisson distribution. So this is the same as 1 minus P, D equals 0, minus probability of D equals 1. And now the definition of Poisson distribution, so that's e to the minus 0.4 minus 0.4 to the power of e to the minus 0.4. Or we can just plug this into our calculator or look at the statistics tables to get the answer. So the answer to this is 0.06155. I'm going to use the unrounded figure because I'm going to use that later on in our calculation. So I've worked out now the probability that in any day, the number of cores is more than 1. But now I'm interested in finding out at least 20 of those in a sample of 250. So let me repeat. So team leader is looking at 250 summer days, and he's interested in getting more than or equal to 20 of these days with this probability of success. Now I'm going to introduce a new random variable. Let's call it S for summer. So there are 250 events, and the probability of success, as we just worked out, is 0.6155. So we've got a certain number of events, and we know the probability of success. So how do I work out the probability that I've got at least 20 success events? This follows a binomial distribution. So that's a binomial distribution because I've got 250 days. I want to see what's the probability of at least 20 days, which gives me what I'm after, which is more than one call for help. And the probability that we want to work out is what's the probability of S greater than or equal to 20. Now, we could use a calculator to work this out, but the question is asking us to use a Poisson approximation. We know that in a binomial distribution, when the n is big and the p is small, in this case, yes, n is big 250, p is small, is 0.06155. We can approximate that. So S approximately equals to a Poisson distribution with the parameter or the mean equals NP. So N times P. So this is my Poisson approximation. So therefore, S approximately follows the Poisson distribution with parameter 15.388. Now, what is the probability that S is greater than or equal to 20? That's the same as the probability that S is less than or equal to 19. Again, using our calculator, 1 minus 0.8525. So the probability rounded to 3 significant figures is 0.148. And that's the probability of the leader finding at least 20 of these days when more than one call for help was received by Team A. There are 3 parts to this question. First of all, is to work out the probability of success, the P. Secondly, is to write down this binomial distribution. And the third part is for us to use the Poisson approximation to find out the distribution of S to get the probability that's asked for in the question. Now let's look at part C and read the question together. Mountain Rescue Team A believes that the number of calls for help per day is lower in the winter than in the summer. The number of calls for help received in 42 randomly selected winter days is 8. The question is asking us to use a suitable test at a 5% level of significance to assess whether or not there is evidence that the number of calls for help per day is lower in the winter than in the summer. And we're asked to state our hypotheses clearly. Whenever we're asked to do hypothesis testing, we need to know whether we're using a one-tailed test or a two-tailed test. So the clue is in the question. It's been given to us a couple of times. Lower in the winter than in the summer. So the question is asking us to test whether the number of calls for help per day is lower in the winter than in the summer. The other thing to remember is the duration. So the question has given us the number of calls or the rate of 0.4 per day. But what about in part C? In part C, we're looking at 42 random days. Again, we need to be adjusting the mean in the parameter in the Poisson distribution. Let's do part C together. I'm going to name a new random variable, W for winter. And I'm going to say that, well, W follows a Poisson distribution with mean or parameter lambda. So let's work out lambda and what that should be based on the 2 hypotheses. For the null hypothesis, we think that there's no difference between the summer call rate and the winter call rate. So the null hypothesis, then remember, we're looking at 42 days here. Therefore, lambda equals 42 times 0.4, which is 16.8. For the alternative hypothesis, however, what is lambda? Are we saying lambda does not equal, or lambda is less than, or lambda is greater than? Again, blue is in the question. It's asking us whether in the winter, lambda is whether it's lower in the winter. So lambda less than 16.8. So these are our hypotheses. And what is the probability that we need to be working out? Let's look back at the question. It's asking us to work at a 5% level of significance, and it's given us the data. So in 42 days, the number of cores was 8. What's the probability that W is less than or equal to 8? And we're going to see whether that's less than 5%. Plugging that into a calculator, lambda equals 16.8. This gives us 0.0141. So less than 0.05 is a one-tail test. So let's write that down there, one-tail test. So it's less than our critical value. Therefore, there is sufficient evidence to reject H0. Essentially, we're saying rate of course is lower in the winter. And that's our answer to part C. Let's look at part D together. In the question, it says, during the summer, Mountain Rescue Team B, so a different mountain rescue team, receives calls for help randomly with a rate of 0.2 per day, independently of calls to Mountain Rescue Team A. So the calls don't affect each other. The random variable C is the total number of calls for help received by mountain rescue teams A and B during a period of N days in the summer. On a Monday in the summer, mountain rescue teams A and B each receive a call for help. Given that over the next N days, the probability of C equals 0 is less than 0.001, we are asked in part D to calculate the minimum value of N. Right, okay, so there's quite a bit in the question, so let's try and break it down. Let's try and write down in mathematical notation what we know from the question. The important thing for us to first of all note is that we've been given the rate of calls for rescue team B of 0.2 per day, but then in the question itself, it talks about N days in the summer. So again, we can assume that the calls happen independently of each other in different days. And then we can write down the distribution for the calls happening for team B. And I'm going to name a couple of variables. So first of all, you may remember from the earlier part of the question that we had D. So D was the number of calls received by team A per day. The per day is important because it affects parameter in our distribution. So in one day, we expect that team A received D number of calls. And let's call our next variable E. And we define that as the number of calls received by team B per day. Okay? So that is our variable per day. But the question is asking us about N days. So how do we get the distribution and the parameter for the calls per N days? Now, you need to know that for a Poisson distribution, if the events are independent of each other, we can simply multiply the number of calls per day by the number of days. Therefore, I'm going to call some new variables again. So for Dn, it's going to be number of calls received by team A in N days. And for En, E little n, I'm going to define that as the number of calls received by team B also in N days. So I've got the variables that I'm interested in right now. And let's look back at the question. The question says the random variable C is the total number of calls for help received by mountain rescue teams A and B during a period of N days. So we know that C equals Dn plus En. That's what's given in the question, the definition of C. And the question gives us an inequality, the probability of C equals 0. Let's have a think to see whether we can work out the distribution of the random variable C. Now, random variable C is the sum of two random variables, Dn and En. And we know that Dn and En represent the number of calls received by team A and team B over N days, respectively. Again, we assume that the events are independent. And again, a property for the Poisson distribution is that if D follows a Poisson distribution with mean 0.4, then dn over n number of days simply follows a Poisson distribution with mean 0.4 times n, because we've multiplied that by n number of days. Very similarly, E follows a Poisson distribution, so we've been given that in the question. So that's the number of calls received by team B per day. So it follows a Poisson distribution with mean 0.2, and over n number of days, so E little n follows a Poisson distribution with mean 0.2n. So we've now written out the distribution for En and Dn. What about C? C is a sum of the two random variables, Dn and En. Again, a property of the Poisson distribution is that we can simply add the means of these two distributions. Therefore, C follows Poisson distribution with mean 0.4n plus 0.2n, because Dn and En are independent of each other. Okay? Simplifying that, C follows the Poisson distribution with mean 0.6n. Looking back at the question, it's given us this inequality. Probability of C equals 0 is less than 0.001. How do we evaluate the probability of C equals 0 in a Poisson distribution? You have this in your formula booklet, but you may know that by heart anyway. If X follows a Poisson distribution with mean lambda, then the probability of X equals small x is simply e to the minus lambda, lambda to the power x, and x factorial. Therefore, probability of C equals 0 is e to the minus lambda is 0.6n, lambda to the x, because x is 0, that's 1, and then it's 0 factorial, which equals 1. Simplifying this inequality, we get e to the minus 0.6n is less than 0.01. Taking the natural log both sides is minus 0.6n is less than the natural log of, oops, it should be 0.01, 0.01, natural log of 0.001. And then dividing both sides by minus 0.6, and because we're dividing by a minus, we need to reverse the direction of the inequality sign. So log of 0.001 over minus 0.6, which means that n is greater than 11.5, working out this in the calculator. And because n needs to be a whole number, therefore the minimum value of n needs to be 12. So n is greater than or equal to 12. That's the minimum value that we need for n. N could be 12, could be 13, could be 14, but can't be 11 or less. So that's our part D. That was our part D. Let me just make this smaller and try and answer part E. We don't need a lot of space. It's just a 1-mark question. It's asking us to write down an assumption that needs to be made for the model to be appropriate. Often when we look at Poisson distributions, we need to assume, as I said a number of times when we were answering part D, is that we need to assume that the events, for example, the number of calls, are independent of each other. So a call that I have right now, let's say at 9 o'clock in the morning, is not going to affect the distribution of calls later on in the day. And also another word that we could be using is that the number of calls are independent and rate is constant throughout the day. So it's not going to change. For example, the 0.4 per day for calls that team A receive, it's not going to change. 0.2 calls per day that team B are going to receive are not going to change in one day and over a number of days. So independent and constant are the two words that the examiners will be looking for.